Hello everyone. Greetings. This is a presentation on the benefits that accrue to foundries and society from optimization of the casting process. It focuses on energy and material savings, and reduction in pollution. A few SoftCAST case studies, of simulation and improved methoding of investment castings, are used to illustrate these benefits. This document draws some of its content from 1. A presentation made by us at the SEPT 2018 WFC in Krakow, and 2. A corresponding paper originally published in the November 2019 issue of the Foundry Trade Journal, UK, which holds the copyright. The materials are used here with permission from the 73rd WFC and FTJ, UK. We acknowledge these sources with thanks for the same. Before we dive into some of the investment casting case studies, we take a quick look at the huge variety of investment castings that have been simulated in SoftCAST. Apart from their trees also being simulated and evaluated, in many cases, their method designs were also developed or improved in the system. A small snippet of this variety is displayed in this slide. Our study focuses on the energy savings and reduction in carbon emission in the IC foundry industry, that result from quality and overall yield improvement. Each case covers method improvement, that is, quality and yield improvements, based on simulation of the casting and its existing method design, followed by system-driven design of a new or improved method, validated by simulation. Note that another study, SoftCAST IC Case Studies, Set 1, documents the specific financial benefits derived through SoftCAST, by 4 customers. This is based on a detailed analysis of 10 casting projects, whose data was provided by those 4 IC foundries. You are invited to peruse the document for detailed information on financial gains that accrue from SoftCAST. The study uses findings from a U.S. research project that computed the savings in energy consumption and reduction of pollution, from a 5% improvement in yield, across a variety of cast alloys and processes. Data from 4 IC units in India and 1 in Hungary, pouring steels, nickel alloys and copper alloys, was analyzed. The castings ranged from a 1 kg steel component to a 40 kg nickel alloy component. The parametric rates of savings in energy consumption and pollution, as deduced from the U.S. study, were used to estimate the corresponding savings that accrued to these 5 IC units, as a result of the quality or yield improvements through SoftCAST. Our first case study pertains to the savings from a quality improvement project of a 7.7 kg CF8M knife edge valve body casting. This project was for a medium-sized IC foundry in Western India. The first step was to perform a casting simulation, the results of which, that is hotspots, temperature maps and thermal traces, clearly showed the defect potential, the solidification zones, and the required locations of the feeds, that is, gates. The existing method for the knife edge valve body at this investment casting foundry did not assure quality at all, leading to 100% defectives. Simulation of the existing method showed inadequate feed, that is gate design. Feeds were not applied at the locations required. And at the incorrect locations where they were applied, they were incorrectly sized. All this resulted in 100% level 3, level 4 defects. The new method, designed through simulation, delivered 100% acceptable castings. Apart from correct design of the gates and feeder and runner bars, the casting orientation in the tree was also changed. This method was used in subsequent production runs. Our second case study is a quality improvement project for a 6.5 kg gunmetal ring casting. This was at a medium-sized IC unit in Western India. The results of the casting simulation, the first step generally performed, that is hotspots, temperature maps and thermal traces, clearly showed the defect potential, the solidification zones, and the required locations of gates. The foundry was experiencing defects with their existing method. Simulation of the method showed inadequate gate design. Feeds were not applied at the locations required. And at the incorrect locations where they were applied, they were incorrectly sized. All this resulted in 100% level 3 and level 4 defects. The new method changed the orientation and provided correctly designed gates at the required locations. The rest of the tree, that is the feeders and runner bar, was also redesigned. This method delivered 100% defect-free castings. Our third case study is a quality improvement project for a 1 kg planetary cage alloy steel casting. This was at a medium-sized IC unit in North India. Results of the casting simulation, that is the hotspots, temperature maps and thermal traces, clearly showed the defect potential, the solidification zones, and the required locations of the gates. The existing method for the planetary cage casting at this IC foundry did not assure quality at all, leading to 100% defectives. Simulation of the existing method showed inadequate feed design, resulting in significant isolations and equilibrations. The new method, designed through simulation, provided correctly sized feeds at the required locations, and delivered 100% acceptable castings. This method was implemented after one trial. Our fourth case study is a quality improvement project for a 2.5 kg WCB valve body casting. This was at another medium-sized IC unit in Western India. The first step was to perform a casting simulation, the results of which, that is the hotspots, temperature maps and thermal traces, clearly showed the defect potential, the solidification zones, and the required locations of the gates. The existing method for this valve body casting did not assure quality at all, leading to 100% defectives. Simulation of the existing method showed incorrect feed design, which was the cause of the level 3 defects. The new method, designed through simulation, provided correctly sized and shaped feeds at the required locations, and delivered 100% acceptable castings, along with a higher yield. This method was implemented without any trial. Our fifth case study is about the development of a new investment cast component, called end section. This 40 kg component was required to be manufactured in Hastalloy, a CY40 nickel alloy, to aerospace quality standards. The results of the casting simulation, that is the hotspots, temperature maps and thermal traces, clearly showed the defect potential, the solidification zones, and the required locations of the gates. Based on the results of the casting simulation, a few options on the method designs, that is the gate locations, gate size and shape, and the design of the feeder and runner bars thereafter, were developed. Before adopting a final casting technique, the method designs or trees were simulated to check their effectiveness. Simulation of the trees helped in finalizing a design that was robust and promised 100% defect-free castings. This was borne out by the shop floor results after actual implementation. These 5 case studies show the considerable benefits that accrue to the foundry by using the SoftCAST simulation and methoding system. Overall yield improvement resulted from 2 sources: 1. Method yield increase, and 2. Indirectly through quality improvement, and thus through reduction or elimination of rejects, and reduction in repairs. Overall yield improvement ranged from 30% to 50% across these castings. Reduction, and in some cases, elimination of shop trials, was yet another benefit that the foundry secured through the use of SoftCAST. A secondary benefit was the reduction in carbon emission, a direct fallout of the reduction in material and energy consumption due to quality and yield improvement. Green Foundry was thus enabled. These case studies also show the considerable benefits that accrue to society due to the optimization of casting manufacture through SoftCAST. Energy savings ranged from 10 kWh to 400 kWh per cast product and per shop trial reduced, for the 1 kg planetary cage and the 40 kg nickel component respectively. Besides, in the latter case, Since less number of buffer castings needed to be produced, there was a saving of 3,000 kilowatt-hours. Pollution reduction, as measured by reduction in carbon emission, ranged from 3 kilograms to 95 kilograms per casting correspondingly. Further, in the case of the end-section casting, the less number of buffer castings that needed to be produced contributed to a CER reduction of about 670 kilograms. All this contributed to a green environment and green society. These benefits of quality and yield improvement, and reduction or elimination of shop trials, resulted in considerable financial and other gains that these IC units secured in real terms. This indicates that the use of SoftCAST would be one way of improving the financial and business situation in the IC foundries. You may also refer to another study named SoftCAST IC Case Studies, Set 1, that documents the specific financial benefits derived through SoftCAST, by 4 customers. This is based on a detailed analysis of 10 casting projects, whose data was provided by those 4 IC foundries. Assuming that difficult economic and operational situations could keep coming up, foundries would be well advised to look into ways and means of reducing costs while meeting customer requirements. The SoftCAST simulation and methoding system would greatly contribute in these endeavors, by way of significant financial benefits as also contribution for growth. Further, we also conclude that the SoftCAST simulation and methoding system is an invaluable aid for reducing material and energy consumption, which in turn results in considerable reduction in carbon emissions, a significant benefit for society. Our conclusion: there are considerable benefits to be secured by foundries and society, through the use of SoftCAST. The corresponding significant positive impact on financial benefits, material energy consumption, and CER, ensures green and profitable investment castings. As stated at the start, this document draws some of its content from 1. A presentation made by us at the September 2018 WFC in Krakow, and 2. A corresponding paper originally published in the November 2019 issue of the Foundry Trade Journal, UK, which holds the copyright. The materials are used here with permission from the 73rd WFC and FTJ, UK. Thank you for your time and attention. We would be happy to provide any more information needed.